Okay, so in the previous two examples, we converted from a drug rate, okay, into a flow rate. And then likewise in the previous example, in the previous video, we converted the flow rate of the IV into a drug rate. So let's go and look at the next example, and it says that we have an order for ampicillin sodium, 500 milligrams IV piggyback every 6 hours to infuse in 15 minutes. And the problem simply says to find the dosage rate of this antibiotic in milligrams per minute. Okay, so this is slightly different than the two previous examples. Okay, so you notice that some of the information is missing. Okay, we don't know the concentration of the drug in the bag. Okay, in fact, we don't need it. Okay, so for something like this, we want to avoid overcomplicating the problem, right? Making it harder than it really seems. Okay, so we have the amount of the drug. We have the time the drug is supposed to infuse, right? The IV is supposed to infuse, which is 15 minutes. All right, and it's asking for the dosage rate in milligrams per minute. Okay, so remember, right, that a dose rate is equal to the amount of the drug divided by time. Okay, so that's what we're going to do. We're going to take the amount of the drug, which is 500 milligrams. All right, and then divide it by the amount of time, which is 15 minutes. All right, and we can punch that on our calculators. So 500 divided by 15. Okay, it's not a nice whole number. It says repeating decimals, 33.33333. Okay, so let's go and round it to the nearest whole number. Okay, so to the nearest whole number, this is equal to 33 milligrams per minute. All right, and that'd be the final answer. Okay, so we have the drug rate in milligrams per minute, and we're finished. So 33 milligrams per minute is the dosage rate. Okay, that completes that example. So let's go to look at the next one. So it says a patient with a systemic infection must receive 500 milligrams of ampicillin sodium IV over 60 minutes. It says that the concentration of the IV solution is 30 milligrams per milliliter. All right, and the problem wants to know what is the flow rate of this antibiotic in micro drops per minute. So remember MC means micro, and then GTT stands for drops. So MCGTT stands for micro drops. Okay, so we want to find the flow rate of this antibiotic drug in micro drops per minute. Okay, so we have 500 milligrams over 60 minutes. So that's the amount of the drug the patient will receive over 60 minutes. Okay, right, and is equal to how many micro drops per minute. Okay, so first of all, right, when it says micro drops, right, what does it mean by micro drops? Okay, so let's go back to chapter 10. Okay, so going back to chapter 10, so we're looking for table 10.1, and it should be near the beginning of chapter 10. All right, so here's the table 10.1 on common drop factors. Okay, so for macro drops, okay, which depend on the tubing being used, right? 10 drops could be 1 milliliter, 15 drops could be 1 milliliter, so on and so forth, right? So those are macro drops, and they depend on the tubing. Now, when it says micro drops, okay, micro drops is universal. So it's the case that 60 micro drops is equal to 1 milliliter, and that's always the case. Okay, so the tubing that uses micro drops, right, the universal calibration of the tubing, so to speak, would be that 60 micro drops is equal to 1 milliliter. Okay, so that's what we're going to use to do this problem. Okay, so remember that 60 micro drops, okay, is equal to 1 milliliter. Okay, so we're going to start with the 500 milligrams over 60 minutes. So 500 milligrams. So let me start that over again. So 500 milligrams of the drug will be given over a 60-minute period. Okay, so that's going to be our dosage rate. So let's not worry about simplifying. Let's just leave it as 500 over 60. Okay, so we don't know how many milliliters are in the bag, but it does tell us the concentration, that 30 milligrams are in 1 milliliter of solution. Okay, so let's go ahead and convert this. Okay, by multiplying by 1 milliliter. Okay, so we're going to invert the concentration. So 1 milliliter goes in the numerator. Okay, and 30 milligrams in the denominator. Okay, so we multiply by 1 milliliter over 30 milligrams. All right, we're going to eliminate the units of milligrams. Okay, and that'll give us the flow rate in milliliters per minute. Okay, so on our calculators we can do 500 divided by 60. Okay, that's going to be a decimal number. Let's not worry about that. Do not round that number there. Okay, leave it as 8.3333. All right, and we're going to multiply by 1 divided by 30. So multiply, okay, so I'm sorry, multiply by 1 and then divide by 30. All right, or you can divide by 30. All right, so multiplying by 1 has no effect. So you're going to take 8.33333 divided by 30. Okay, we get that funky decimal number. So 0.27778 at the end. Okay, so that's equal to 0.2777, so with the 7's repeating, with an 8 at the end, milliliters over minutes. Okay, so again, even though this is a funky number here, funky decimal, we're not going to round it because this is not the final answer, right? Our final answer should be in drops per minute. So again, this is a flow rate, okay, in milliliters per minute. Okay, it's an extremely small flow rate in milliliters per minute. So 0.2777778 milliliters per minute. Okay, so we're not done until we get the units of micro drops per minute in our final answer. Okay, so we know from chapter 10 that 60 microdrops is equal to 1 milliliter. Okay, so once more we're going to multiply by 60 microdrops. That's right, so MCGTT for microdrops. All right, over 1 milliliter. All right, the reason that the 60 microdrops goes on top of that fraction is because we want microdrops in the numerator, and then minutes in the denominator. We already have minutes in the denominator of this fraction here, right? Milliliters per minute. Okay, so the units of milliliters are eliminated in the process. Okay, so again, without rounding this decimal here, the 0.27778, okay, we're going to multiply that by 60, right, to get the final answer. So multiply that by 60. All right, and if necessary, we will round this answer to the nearest whole number. So it's 16.666667. Right, so when you round it to the nearest whole number, it's equal to about 17 microdrops per minute. So the final answer is equal to 17 microdrops. Okay, per minute. All right, and that's the final answer. So this is the flow rate of the IV. Okay, so for the patient, in order for the patient to receive 500 milligrams over a 60-minute time period, okay, the IV must be flowing at approximately 17 microdrops per minute. Okay, that completes this example. Okay, so before we go on to the next example, let's quickly review the one we just finished. Okay, so we took the amount of drug, which was 500 milligrams, and divided it by 60 to get the drug rate. But keep in mind, if you put that in your calculator, right, 500 divided by 60, all right, you're gonna get a nasty decimal. Okay. So remember, so since this is not the final answer, right, you're just gonna leave it as 500 over 60. All right, although you can simplify that fraction as much as you want to. All right, so then we multiplied it by the reverse of the concentration. So the concentration given in the problem was 30 milligrams per 1 milliliter. So when you invert it, right, it becomes 1 milliliter over 30 milligrams. So we multiply this fraction, 500 milligrams over 60 minutes, multiplied by 1 milliliter over 30 milligrams, right, so that we have the flow rate in milliliters per minute, which is this number here. Once again, since this is not the final answer, do not round this number. Okay, include as many decimal places as you can. All right, so then we multiplied that by the number of microdrops in 1 milliliter. Okay, so since we want our final answer in microdrops per minute, right, the 60 microdrops has to go on top of that fraction, and then the 1 milliliter on the bottom. Okay, so this decimal here, 0.277778 multiplied by 60 microdrops per 1 milliliter, right, eliminates the units of milliliters, and then we get our final answer rounded to the nearest whole number, which is 17 microdrops per minute. All right, and that's the corresponding flow rate of the IV. The next example says the physician ordered Platinol, 100 milligrams per meter squared, IV, to infuse over 6 hours, once every 4 weeks, for a patient whose BSA, body surface area, is 1.66 meters squared. All right, so the question has two parts, and the first part of the question asks how many milligrams of this anti-neoplastic drug should the patient receive? Okay, so the first part of this question is an application of this formula here, which says that the size of the patient multiplied by the rate given in the order is equal to the dose. Okay, so the size of the patient is expressed in meters squared. So we're going to type in 1.66 meters squared. All right, and multiply that by 100 milligrams per meter squared. Okay, so when we do that, we get the amount of the drug, the dose, okay, the amount of the drug the patient will receive, so we eliminate meters squared in the process. Okay, so on our calculators we do 1.66 multiplied by 100. Okay, and we get 166 milligrams. Okay, so that's the amount of the drug the patient will receive. Okay, the second part of the question says if the dose of the drug were administered in 1,000 milliliters of D5, half normal saline, so 5% dextrose and water, including the half normal saline. So at how many milliliters per hour would the IV run? Okay, so once again, don't overcomplicate the problem because there's a lot of information going on here, right? We have the volume of solution, okay, 1,000 milliliters, and then we have the time in which to infuse, for which the infusion will take place, which is 6 hours. Okay, so remember, flow rate is equal to volume divided by time, and that's all we have to do, right? So 1,000 milliliters, okay, over 6 hours will give us that flow rate in milliliters per hour. All right, so we're going to punch that in our calculators and then round as necessary. So 1,000 divided by 6. Okay, so round it to the nearest whole number. So 166.66667 when rounded to the nearest whole number is 167. Okay, so the flow rate is 167 milliliters per hour. Okay. Okay, so that's the flow rate at which the IV will run. Okay, and then the first part of the question tells you how much of the drug to add to the IV, or how much to include. Okay, so we didn't need to use this information to answer the second part of the question. So the answer to the second part of the question, all we needed to know was the volume of solution and the amount of time.